Hello everyone and welcome to this tutorial. My name is Kem-Meka and in this video I'm going to talk about the shape of data. But before that, let's try to solve this small problem. Imagine that I perform an experiment and collect my data and they are depicted in this figure. I would like to know the relationship between the feature. We can see that when X increases, Y increases as well. So there is a strong linear correlation between my variables. Linear regression in this case allow me to get this line of best fit, which is the shape of my data. This line can help me, for example, to do some prediction or more generally to build predictive model. What if my data are no more linear? For example, this one on this figure. You can see that linear regression can no more be effective for this kind of data. And it is even harder when I am in high dimensional, let's say dimension greater than 4. Therefore, we need a method that helps us to discover the shape of my data. This is when topological data analysis come into play. Topological data analysis uses the notion of homology to deduce the shape of the given data. Homology is just an algebraic object that assigns to data a certain number called signature or Betti number, and that gives me an information about the shape. For example, if my data is just a point, the Betti number 0 will be 1, the Betti number 1 will be 0, the Betti number 2 will be 0, the Betti number 3 will be 0, and all the rest of Betti number will also be zeros. If my data is instead a torus, my Betti number 0 will be 1, my Betti number 1 will be 2, my Betti number 2 will be 1, and all the rest of Betti number from 3 will be 0. So when I have my data, I can always compute Betti numbers to detect the shape of my data. But there's a problem. Real-world data do not always come with very nice shapes and smooth, well-formed shape like this one for us to compute the homology and detect the shape. Real-world data usually come as a point cloud in some Euclidean space, and it is then our task to build object on top of it, and these objects are called simplicial complexes. To define the notion of simplicial complex, we need first to know the one of simplicity. A n-simplex is just a convex whole of n plus 1 affinely independent point. In other words, here I have my point v0, v1 up to vn. Satisfying this formula star, I will say that they form a n-simplex. For example, a 0 simplex is just a point. A 1 simplex is just an edge. A 2 simplex is just a triangle. A 3 simplex is a tetrahedron. Then now define the notion of simplicial complex. A simplicial complex is just a finite collection of simplices satisfying A and B. For example, on the left-hand side here, I have a valid simplicial complex. On the contrary, on the right-hand side, I have here a invalid simplicial complex because you can see here that the intersection of these two simplexes are no more a simplex in both. Since I know already the notion of simplicial complex, let's give this workflow. We will always start with data which are point cloud. We will have to build simplicial complex on top of it, which correspond to graph, therefore a geometric object. Having the simplicial complex, I can compute the so-called chain complex, which is a vector space associated to the n simplices. Having the vectors, having the chain complex, which is the vector space, I can compute the homology group, which is also an algebraic object, and which is defined as a quotient vector space.